Today I want to talk about continuous distributions. So please open up in your study guide to the continuous distribution section. Now let's begin with the definition of a continuous random variable. Continuous random variables are basically measurements. When we talk about measurements, we typically are using continuous random variables to represent those measurements. Continuous random variables are numerical variables whose values fall within a range or an interval. And continuous random variables can be described by density curves. So in the last section we studied about discrete variables that took on only whole number or integer type values, and there was no in-between values at all. Now we're going to take a look at continuous random variables in this section, and remember, continuous random variables typically represent measurements of some type. When we look at continuous random variables, we're looking at numerical variables who fall within a range or an interval of certain values, and they can take on all of those possible values within that particular range. We like to graph continuous random variables with density curves. So density curves will be used when we're talking about continuous random variables. Now let's talk about the density curve itself. Now a density curve is always on or above the horizontal axis. The density curve also has an area equal to 1 underneath it. The density curve often describes an overall distribution. And finally, a density curve describes what proportions of the observations fall within each range of values. These are four very important definitions of a density curve, and we're going to be taking a look at many different types of density curves that are going to be associated with probability distributions. Now once again, a density curve will always lie on or above the horizontal axis, because the area underneath the density curve is going to represent probabilities, and we know probabilities will always be positive. The density curve will always have an area of 1 underneath it, and recall that the sum of all probabilities in a probability distribution is equal to 1. Therefore, a density curve will always have an area equal to 1 underneath it, regardless of the shape of the density curve. Now, a density curve once again often describes an overall distribution, and it describes an overall distribution by its shape. It gives us an idea of where the heaviest probabilities fall, where the most likely outcomes fall, and where the least likely outcomes will fall. And finally, a density curve will allow us to describe what proportions of observations fall within a range of values. So when we're looking at probabilities of certain ranges or intervals, we are associating those with a particular density curve and its probability distribution. Now we're going to begin by first looking at unusual density curves. These density curves really have no name, but they do take on sometimes unusual shapes. A density curve can be any shape. Here's an example of a density curve that's in the shape of a triangle. Unusual density curves are generic continuous distributions. Once again, the random variable x can take on any range of values within the domain of possible values. In unusual density curves, probabilities are found by calculating the area underneath the curve. Recall that a density curve has an area of exactly 1 underneath it. So any slice or portion of the density curve can be found by finding the area underneath the density curve itself. Now let's take a look at example 1. Now in these examples of unusual density curves, we're going to look at some real basic geometric type shapes. Now unusual density curves can take on any shape, and typically they're not defined by functions. Now suppose that we have the following unusual density distribution. Notice the area underneath this curve is equal to 1. Our unusual density distribution is a right triangle here. And notice that we can take 1/2 the base times the height. The base being 4 and the height of this triangle being 1/2, 0.5. If we take 1/2 times 4 times 0.5, we get an area of 1 underneath it. This particular shape defines a proper density curve because the area underneath this curve is equal to 1. Now suppose we want to find the probability for this particular unusual density distribution that the random variable x is less than or equal to 2. Now this region would be represented by the green shaded region as drawn. Now to find the area of this particular region, or the probability that x is less than or equal to 2, we simply find the area of the shaded green triangle here. And that area once again is 1/2 base times height.